Today we will talk about multidimensional arrays. Let's start first with arrays. A quick, brief recap of what an array is. So, an array is defined as a collection of elements of same data type stored in a sequential fashion in the memory. So suppose we have elements as 10, 11, 12, 13, 14. Okay. All these elements are sequentially stored at the index 0, 1, 2, 3, 4. So we call this as a 1D array. This is my 1D array with a length equal to 5. And if I have to access any element of this array, suppose I call this array as A, and I have to access any element of this array, I will use A with a square brackets, and I'll mention the index of that specific element. Let's say we want to talk about this particular element 12, so we will use A of 2. So A of 2 will return the value 12. Now this particular array has only one dimension, right? There is only one dimension to it, and the length of that dimension is 5. What if we have more than one dimension? So suppose we have a matrix. Okay. This is only for representation view. The only thing that array ensures is that the memory will be allocated will be in a contiguous. So it's a contiguous memory which is allocated. But in memory, it might be stored in a sequential. It doesn't matter. It's just that it has to be contiguous. Okay. So here, suppose I want to store these elements 1, 2, 3, 4 up to, and similarly 12. This will be 5, and so on. Like you can fill the dots here, right? So I have these elements to be stored. Now here, this is a matrix which has 2 dimensions, right? So one dimension specifying the number of rows, the second dimension specifying the number of columns. So this is a matrix of size 3 cross 4, where 3 is the size of your rows dimensions and 4 is the size of your second dimension. So as an array, if you want to represent it as an array, we will use the notation A with 2 square brackets, each mentioning the dimension of that specific dimension. So here it will be A of 3 or 4. So which means it will have, the first dimension will have a length of 3, the second dimension will have a length of 4. Now suppose we have 3D array, which can be visualized again for just understanding purpose, which can be visualized as multiple matrices stacked. Okay. And right, so this can be seen as there are so many matrices just stacked in this direction, right? So we can call, let's say we have 3 cross 4 matrices again, and there will be, let's say, 5 such matrices. So now this can be represented as a 3D array A, which will have now 3 square brackets, each representing one dimension, and the sizes of them will be 3, 4, 5. Okay. So similarly, we can have more dimensions added to the array. So the a way to define an array in general is basically have the name, add as many square brackets as many dimensions you want in that array, initialize each dimension with the size of that particular, fill the value in that square bracket as the size of that particular dimension. Okay, so now let's talk about how to store the elements in this array. So starting with 1D arrays. So it's the simple way to store elements in an array A. So you have to define the size. Suppose I define A of 10 and it's of type n, which means that this is an array A, which will be storing at max 10 elements and will be of data type int. So one way is that I can take as an input from the console and start storing the arrays. So though the array can store 10 elements, index will start from 0 and will last up to 9. So it would be I less than or equal to 9 or I less than 10, I plus plus. And for each element, we will take the value using scanf %t, comma, address of A of I. Right? In case you already know the elements of the A while writing the program itself, you can simply do this, right? So you can do this A equal to 1, 2, 3, 4, 5. So in this way, I have already told how many elements to be allocated in the memory in this array. Now, suppose if I mention this as A of size 10 equal to these many elements. So the number of elements which I have assigned is only 5, but the size of this array has been declared 10. So actually, the array A will now be storing the values as 1, 2, 3, 4, 5, and the remaining 5 elements will be 0 because we have not assigned anything. So they take the default value of 0. Okay. Similarly, for 2D arrays, to take the input from console, we will need 2 loops. One is for I equal to 0, I less than size of dimension 1, I plus plus, where D1 will be the size of the first dimension depending on what is the size of video. And similarly, for second dimension, we will have another loop, J equal to 0, J less than D2, J plus plus, and we will take the value of the scanf, which will assign the value of %t in the array at A of I and the index j. Okay. Okay. So now you can close these spaces. So this will again assign a matrix. Like this is how you can take a matrix as an input from the console. Similarly, for 3D arrays, in this function, just add one more loop here. Add one more loop, which will be the next play for k equal to 0, k less the dimension of the size less than the size of the third dimension, k plus plus. Okay. And instead of scanning of this ij, we will introduce one more with k here. Okay. This is how we can take the input in a 1D dimension, 2D dimension, and 3D dimensional arrays using console. Now, suppose we know the number of elements to be assigned in an array during runtime itself. So how can we do it? So we can say that A of 2 and 3. So this says that it's a 2D array with 2 rows and 3 columns. And the elements has to be like this. Okay. So now what will happen in this matrix? The elements will be actually assigned in a row measure format. Sorry. So it will be 1, 2, 3, 4, 5, 6. So this is how the elements will be assigned in it. Suppose I had, instead of 2 rows, So 2 rows, I have 4 rows. Then the elements of the matrix A would have been, for the same value, would have been the rest assigned to 0. Suppose instead of 3 columns, here I have the value is 4 columns. Okay, then the assignment would have changed. So then in that case, assignment would have been 4, 5, 6, and rest as zeros. This is one way of assigning the elements. The other way is that we itself define what should be the elements of each row. So suppose instead of this, we define, like we write it as 1, 2, 3. So I say that my first row is an array with elements 1, 2, 3. My second row is an array with element 4. My third row is an array with elements 5 and 6. So with this initialization, the elements of array A of size 4 cross 4 will be like 1, 2, 3, 0, 4, 0, 0, 5, 6. The remaining elements is 0, and the remaining rows is 0, 0. Okay, so we can do the initialization during writing the program itself in case we know what elements to be assigned. If we don't know those elements, then we can take them as an input during runtime. Now, this is, again, you know the memory at runtime. Okay, you knew that there will be 4 rows and 4 columns. Okay, but what if I don't know the memory at runtime? Memory at writing while I'm writing the program, and the required memory will only be known during runtime. So suppose I have to store an array of A of size and M. How can I store this array without assigning some, without defining some big size array of A 100, B 1000, and assuming that my N and M will definitely be less than or equal to this 100 and 1000, which will actually result in saving a lot of memory during runtime, which is not even required. So to overcome this issue, what we can do is we can use function malloc to allocate memory dynamically. What I mean that while the program is running, we will come to know the value of N and M. As soon as we know the value of N and M, we can allocate a memory of size exactly N cross M into size of the data type, whatever we are storing. So suppose if we are storing int, then we can simply call this operator size of int. If we are storing float, we can pass size of float and so on. So we will take only these many bytes, and we will ask the, like we will get only these many bytes of memory allocated from heap. So in the previous case, we were actually saving a big chunk of memory, and it may not always be needed depending on what N and M we have. In the second case, when we are dynamically assigning memory, we are making sure that we exactly allocate the memory required by the program. Okay. How can we do this? Malloc will actually allocate a contiguous memory chunk and will return a pointer to it. So it will be, and then you can type as the pointer to whatever data type you are storing it to. Suppose I want to store this array A of size N and M. So in that case, it becomes int pointer. So this pointer is pointing to a data type of value int, right? So this pointer, integer pointer, is equal to, I'll be using the function malloc to allocate memory of this much size. Now I can just take this and I can put it here. So basically here, what has happened? Now I can use this malloc function. I'll allocate n cross m into size of int many bytes, get a pointer to it, typecast to a pointer of pointing to an integer value, and will store it in this another PTR, reference it by PTR. Now, how to actually allocate the elements. And so now this has actually a continuous chunk of memory, right? But you also want to access it as if it is a 2D array. So how to do that? So you'll have again. So let me take loops from here. Okay. So now, um, so since we are talking about an array, so an array is of size n and n, right? So here I will be less than n, j will be less than n. Now, how to take the value as an input? So simple, scanf, take the value as an int, use the %t as the format here. Now we want the address, exact address we want to store this array. So you can do, so just try to understand it like this, right? So suppose this is an array which has n rows and which has m columns. So it's ijth element, like suppose this element. So which element it will be? It will depend on how many rows were there before it. So suppose these many rows and then this location, right? So suppose the element of this index is I comma j. So it means there were I minus 1. So how many rows would have been there previously? It would have been I rows because the index starts with 0. So it will be I into m. So definitely it has seen that many elements still here and the number of elements to be added here, right? So it will be plus j. Because j starts with 0, so it will have come here. So now whatever the address you will get, we will get the address for this element. So here we can simply do this. Scanf %t. So we were storing here by pointer. Yep. So here we were referencing it by pointer, right? So here it will be PTR. How much we want to shift? I into m plus j. Right. This will be the address at which you want to store. In case you want to access that element, you can directly access the element by taking the value at it. So you can take the value as this. You can use the dereferencing operator, PTR plus I into m plus j to dereference the value. Similarly to printf, you will use this way. And if you want to do any processing, you can simply use the value at this plus 10 and let this be the new updated value you want to store at the same location. So just point it by this. TR plus I into m plus j. Okay. So with this is how we using a malloc, we can actually allocate the memory dynamically to save an array whose dimensions are not known during compile time. Okay. We can look at the examples like a well-documented code as well. So here, if you see, this is the function. So if you see here, maybe I can do something. Yeah. So here is the proper function written here. So we have this defined as r equal to 3, r equal to 4. We call a malloc function to allocate the memory, assign it to a pointer, and we try putting 1 to 12 in that one-dimensional array in a sequence. So we can either do that way, or we can, so if we treat it as a 1D array, then it is simple as like this, because ptr of I is nothing but ptr plus I and the value at it, right? So we can simply do as ptr I of I plus 1. But if you want to treat the same memory as a 2D array, we have to use two loops, one for the row, one for the column. And if you want to print, then we can simply use this one. Okay, I into single string and the value at the point here, ptr. So see here, I'm using the square brackets. So that's why the other way would be asterisk ptr plus I into c plus j. So C here represents the number of columns. Okay. And then once you are done with whatever processing you have to done with this array, you can free the memory, return back the memory to the heap by using the call to free and passing the address of that pointer. Okay. Okay. So with this, now we can look at one simple example of multidimensional arrays. The problem here is that, so the problem here is, suppose we have a maze. Okay, it's a 2D maze. So we are looking at a problem which is using two-dimensional arrays. So we have a 2D binary maze, which stores the value as 1 or 0. Okay, either it will be 1 or 0. And we have to find a path starting from the last element to the first element of the matrix. Okay. And each, if it is a 1, then we can use that cell to move forward in the path. If that cell happens to be a 0, then it's a blockage and we cannot use this cell while traversing. And this maze is some combination of 1 and 0. Okay? And the rest elements are 0. The goal here is to print a path starting from the last element of the array to the first element of the array. So if we see, and we can take 4 kinds of direction. We can go up, we can go down, we can take a right, we can take a left. If it is a 0, then it means you cannot go further. If it is a 1, then you can use that cell and move further. So from here, we go up. It's a 1, we can take a right, and take a right, then go up, and take a right, then take a right, up, then again up, then left, and we get this 2 cell. So it is like up, left, left, up, left, up, left. Okay. While coming downward, it will be just reverse of it, like right, down, down, right, down, right, right, down. Okay. So here, but we are focusing on going from 1 to goal string. So how to solve this problem? Let's simplify it. Let's assume there is only exactly one feasible path. So there is only one feasible path. Or we can put it like this, at most one feasible path. So here it is, at most. Which means either there will be a path or no path. If it is there exists any path, then there will be exactly one unique path. So the question is how we can find this, right? How should we traverse this complete matrix to reach to a goal state? Okay. So we have a 2D matrix, which is very clear to us. So at any element, suppose if we are at this specific location, what are the possibilities? We can go up, we can take a right, we can take a left, we can take a bottom. So if we have reached this specific elements for instance, then what will happen? We can take either of these 4 directions. So once we're at any element I comma j, The four possibilities are you can go to I plus 1 comma j. You can take a left, which is I minus 1 comma j. You can go up, which is I comma. Sorry, I plus 1 comma j is you can go downward. I minus 1 comma j is you can go upward. I comma j plus 1 is you can go right. And I comma j minus 1 is you can go left. And similarly, once you are here, you can also follow these ones. So we will try to solve this problem using a recursion, where our recursive call will be comprising of these four calls at each cell. And the base case will be, if this happens to be a 0, then return 0, like this path. So if you have reached to a cell which contains 0, then it means you cannot proceed further. So you return a 0 and come back. Otherwise, if it is a 1, you go. Again, if you happen to be go somewhere which is not a part of the cell matrix again, then again you trace back. Like for example, if you're here and you take a right, you go to some element which doesn't exist, right? So it's not a valid move. So if such boundary cases arises, then also you return a value of 0. If you happen to be in the goal state, then this is where the search ends. Okay, so with these base cases, let's look at the solution. Let me copy it to notebook so that we can try to understand it in detail. Okay, let's look here itself, and then we will keep on switching. So we get a maze whose dimensions are int m comma n, and okay, let's look at here itself. So we have this matrix here. Okay, this is the matrix which we have. So this is the solution. So if you look at the solution here, starting with the main function, we first take as an input m and n, okay? And once we have taken m and n, we use the malloc function to dynamically allocate the size of m into n into size of int. And we maintain another matrix solution, which is also going to be a binary matrix, which will store the current path in case of cycles. So suppose we have a path which involves cycles, right? So in that case, instead of going again and again through that path, we will store the path. So if we have seen a particular point before in that path, then we will not take the same route again, right? We will just go to the other possibility to avoid that cycle. Now we'll take the input maze from the console and store it. Okay. And similarly, we will assign the solution matrix with 0 because initially we do not know what is the path going to be there. Now let's try to solve this maze util by using this function. It is a very simple function. It's a recursive function. And what it will do, it will take the size of the matrix. It will take the matrix itself. It will take the value x and y, which is x and y is basically your starting point at this point, like at what cell you are right now. So that is x and y. Your solution matrix, which will be storing the path, and your count value, which I'll explain later. So we call the function with m and n, the size of the matrix. The maze itself, we start from the initial position, which is 0, 0. We are trying to find a path from the last cell to the first cell. Okay. And then we have the solution matrix, which is initially assigned to be 0 because we are just starting. And the initial value of the count is 1. Okay. Now, so if this happens to be my goal, right? That is, I have reached the last cell. So in case this is my last cell itself, then, and it happens to be a 1, then we simply return and the solution is here as count. So I'm just, the count here is making sure that in the solution matrix, I know the order of the elements in which they will be occurring, right? Similarly, now if this is 1, it's true and we are done. Otherwise, we check whatever the location we are right now, x comma y, is it 1 or 0, whether it is a feasible cell or is it a blocking cell. So first you have to check that. So remember here, this x and y is nothing but the index of the cell in the matrix, right? So we will check whether this is within the limits. So x should be greater than 0, equal to 0, less than n. Similarly, y should be greater than equal to 0 and less than n. And the maze value at this particular element x comma y should be 1. Now check if this cell happens to be a 1, then we will see whether we have seen this cell before in the same path or not. So basically, now we will look into the solution matrix and we will see whether we encountered the same cell before or not. If not, right, then we will go ahead. If yes, then you will return false, which means that this is not the right cell where you want to look into, and you should consider the other possibilities. If this cell has not been previously explored, then we will go to this cell. So we will add this cell to the solution and we will count, like, so suppose what is the number of this cell we are visiting. So suppose in this example which we were considering for the maze. Okay, let me write another example. So suppose what this was. Okay. In this path, we start from here, right? So in the solution, the final solution we will get, the index of the cells will be, this was my first cell, the second cell of the solution, the third cell of the solution, and the fourth cell of the solution. So that's what this solution of this is storing. So what is the index of this cell in my path? Now, at the specific cell, if this happens to be a 1, I haven't seen this one, I'll take a right and explore first. So I take a right and I explore first. Sorry, this is a mistake. So when I'm doing x plus 1, so I'm taking it downward. The other recursive call will be taking a right. The other one will be taking a left. Sorry. This will be basically going up. Okay. So once you are at a particular cell, you will consider all these 4 exceptions. Like going down, taking a right, going up, and taking a left. So with this, what we will do, we will call the same function because it's a recursive function. So we'll call the same function, but this time we have taken already a down step. So we, instead of I comma j, I have now reached at this specific cell. And now I'm trying to explore whether this cell is feasible or not. Okay. Sorry, the path would have been like this, right? They would have been this path as well. And then similarly, once this is done, if this is not the path, like if I go this, reach here, good. But if this happens to be a 0, then I'll retract and I'll take a right. If this happens to be blocking, then I'll take a back and I'll go down the next recursive call. If this also returns false, then I'll take another recursive call. And if it doesn't go to the goal position, then I will say that the result doesn't exist. Once all the paths have been explored, and I still not able to find anything true, that means I have not able to recover anything. I'll say that this particular cell solution leads to a backend, and so we retreat and we return a false. So it will now return a false to the initial function, and it will consider the other move. If this function at any point was not able to return true, eventually we will return a false here. Okay, and this false signifies that we couldn't find the solution. So just a simple try in here of the same matrix. Okay. So here we start with, right, so we start with this. So this we start with 0, 0. We check the base cases here. The base case is being, is it a goal state? No. Is it true? Yes. Like it's a valid 1, 1. Now, was it there in solution before? No, because it's an empty solution. So I take a downward step. So now with this, I'll take this step 1, 0. So now I'll look at this cell. Is this a goal state? No. Is this a valid cell? No. So it will return a false. And then I'll look at a right step. Okay, which is 0, 1. Is this a valid scope? No. Then I'll take a up step, which is -1, 0. Is this even valid? No. So it will return. Then I'll take a left step, which is again going to be 0, -1, which is not again valid. So if I stick at this cell and there is nothing here, so it's a dead end, right? There was no solution. So eventually this entire function will return false, saying that there exists no solution. Now suppose instead of the 0, we have a 1 here. Then when we take a first this, we go to 1, 0. It's a valid cell, right? So now at this 1, 0, we will take recursive calls. So once we are 1, 0, we will call, we will go take a downward, which is 2, 0, which happens to be a 0, not backtracking. And the next will be going right. So it will be 1, 1. Yes, it happens to be a 1, so it is a tick. And then you will make a recursive call on this function. And this is how you will keep on calling, and then you can just print the path in the while you are doing this, and this will make sure that you have a solution here. Okay, so you are basically printing f this file. So if this happens to be a part of the solution, just print it, and it will be solved. So with this function, you will get the solution starting from the last cell to the first cell of the base. I'll share the code to this problem statement along with the problem description in the video links. I'll also add the details about whatever initializations and information we talked about the arrays in the video description for your future reference. Thank you.